Ladies and gentlemen, this course is all about matrix algebra, or an introduction into matrix algebra, and obviously matrix algebra is very important in modern day breeding. We will be looking at what matrices are, and also some calculations as a means of getting some answers. So basically this course will cover the field of describing matrices, some knowledge as to some of the calculations in matrices and what one can achieve by these calculations, but not a very in-depth study into matrix algebra as one would obviously require from other types of courses. But in terms of how it will assist the animal breeder in modern day animal breeding to utilize this very important tool in their toolkits to enable you to utilize this in animal breeding. So welcome to the course, and let's hope that you can gather enough knowledge so that you get the foundation, so that when we get to more complex models and we get to breeding value predictions, that you will be able to use this tool in everyday life. Good. I think we can get going. The first thing then would be, what is a matrix? And I think one can also describe matrices in common in our days, in our lives as we live. One of the most obvious matrix that I can think of is typically how a calendar would be could be seen. A calendar where you have a month. If you look at a month and you see a month as a matrix, typically the rows in a month would be the weeks. Let's say week 1, 2, 3, and 4, and the columns would be your days, Monday or Sunday to Saturday, if you like. So first day of the week, Sunday, and so forth. So your columns would be your days, and your weeks will be then basically be your rows. One can also see each of these months as a sub-matrix of one big matrix, where you have 52 weeks in, and that would be the year, and your columns will still be the days in each week. So 52 week rows and then the columns. So that's a typically matrix in everyday life, and you can also see here this example where we have a matrix, and we will get to the detail of matrices later on as we move on through the slides. So we will then start off by maybe asking the question, why matrix algebra? Why would one use matrices as a means to calculate things in animal breeding? But one can also say it's a compact notation for describing sets of data and sets of equations. So maybe there's already a clue here in the word equation. We need a lot of equations to enable us to predict the genetic merit of livestock, and we have to use a tool like matrix algebra to enable us to solve all these unknowns of whether one animal will actually breed better progeny than the next. So it's basically then a very efficient method for manipulating sets of data and solving sets of equations. And later on in the course we will get to more detail as to how many equations we need to solve and how many unknowns there are that we have to get the answers for, or the prediction for. So that's basically maybe the reason why we use matrix algebra in the first place, and also just to give a small glimpse into what matrices are. Good, so we have said that the main reason for using matrix algebra would be to use it in solving unknowns in a set of equations. So this is a very small example of where we have three equations. We have the equation 2x minus 4y plus z equals 10, where x y and z is unknown. Obviously, nobody will be able to solve what x, y, and z would be if you have three unknowns and only one equation. But let's say you have a second equation with the same three unknowns in it, 0.3x plus y minus 0.8z equals 5.3. So now you still have your three unknowns, only two equations, but let's say we have a third equation with the same unknowns, 20x plus 18y plus 25z equals 22. So basically we have three equations with three unknowns. Those are the three equations, and our three unknowns are x, y, and z. So if somebody were to ask you what would be the values of x, y, and z, how would you solve that? And you will also realize that it's not really possible to do where you have an equal number of equations and unknowns to solve it by conventional algebra. So you need something in the order, or a tool like matrix algebra, to solve that for you. So we can rewrite, this is just another way of writing those equations in a different form, and we call this different form matrix notation. So we create matrices from these three equations. So we start off by rewriting these equations. So these, we call this a coefficient. So the coefficient here is 2, the coefficient there is minus 3, and the coefficient there obviously is 1. It's 1z, I mean. So by rewriting and then we can rewrite these equations in matrix notation. So this is 2, this coefficient, that coefficient is minus 4, and z's coefficient is 1. That's our first equation's coefficients. The second equation's coefficients are 0.3, 1, and minus 0.8. So that will be our second row in our matrix that we started to create. The third equation then, the coefficients would be 20, plus 18, and plus 25. So we've created what we call a coefficient matrix. It's a matrix full of coefficients. We have 1, 2, 3 rows. We have 3 columns. 3 equations, 3 unknowns. Okay, so that's our first matrix, our coefficient matrix. We then start with our second matrix, and here you can see it's only one column with our 3 unknowns, x, y, and z in a column. And on the right hand side of our equal sign, we have what we have there on the right hand side of the equal sign. So we have basically just rewritten these equations in a different form. So this is the matrices we've just created, our coefficient matrix, our column of unknowns, and on the right hand side of the equal sign, a column of what's on the right hand side. In matrix notation, a multiply is denoted by just a full stop or a point or a dot. So this matrix times that matrix equals our right hand side. And remember, each of these coefficients were multiplied by the unknown. It was 2x minus 4y 1z in our equation, 0.3x 1y minus 0.8 z, so forth. So basically that's the way it's rewritten. That's the multiplication part, and then the equal sign on that side. So basically what we want to know is we want to know what x, y, and z will be. So we can rewrite these equations. We can just sort of move some of them to the other side of the equal sign. So if you want to move this part, coefficient matrix, over the equal sign to the right hand side, to that side of the screen, then obviously you have to divide by it. Now we'll get to that later. You cannot divide in matrix algebra, you can just get the inverse, but we'll get to that later. So basically This is basically the same or rewritten as our unknowns x, y, and z equals to the right hand side times 1 on, or the inverse of our coefficient matrix. So by doing matrix calculations, we can then solve x, y, and z, and we can know exactly what they are. So good, we have now seen that it's possible with matrix algebra to solve or to get the answers for unknowns, given the fact that you have an equal number of unknowns and equations. So let's go and talk about some definitions and how we name certain things in matrix algebra. So you've seen so far that the matrix is basically a rectangular array of numbers arranged in rows and columns. So you've seen in our example we had rows and columns. So it's an array of numbers in rows of columns. And to describe the size of the matrix, we call that the dimension or the order of the matrix. We simply name the number of rows and the number of columns. And it's customary to, if we have a 3 by 4 matrix, it means that it has 3 rows and 4 columns. So you describe the number of rows first and then the number of columns. So it's as simple as that. And then the numbers written into the matrix we call the elements of the matrix. So it's also then possible to describe the exact position of each of these elements in the matrix. So this is just an example where we have a 3 by 4 matrix. Why a 3 by 4? 3 rows, 4 columns. And each of these numbers written into the matrix, each of them, like in this example 13 or 95, we call the elements. And it's also then possible to describe the exact location of the element. So our first element would be in row 1 and column 1. So you have a little you will have a little subscript there to say 1, 1. So, and the 62 would be still in the first row, but the second column. So that would be 1 and 2. So these are the examples. That would be our very first element, would be the first one, first row, first column, 1, 1, first row, second column, and so forth. And second row, first column, second row, second column, and so forth. So that's just a description of the exact location of the element of the matrix. Where is it situated in the matrix? Something else that we need to take cognizance of and know is the so-called transpose of a matrix. Now, a transpose of a matrix is another matrix. So the transpose of one matrix is another matrix that's obtained by using rows from the first matrix as columns of the second matrix. So basically, if we look at this example of matrix A and the transpose of A, and you can see the notation, how we rewrite it. It's an A with a little superscript 1. It's not a 1, it's just a little stripe, and that's the transpose. I'm also certain that you've noticed that we use capital letters if we describe matrices. Good. So here you have matrix A, 3 rows, 2 columns. It's a 3 by 2, so the transpose would be a 2 by 3. So a 3 by 2 becomes a 2 by 3 in this case. So basically your columns will become your rows in a matrix, and that would be a transpose is then 3 by 2 becomes a 2 by 3, like we said. So also a simple thing to note, but that can be very important maybe later on in some of the when we do the calculation. Good. The we also get to some special types or kinds of matrices, and the first special type of matrix would be a vector. It's a type of matrix with only one column or one row, and we call, if it has a column, we call it a column vector. So in this case we have a 3 by 1, and a row vector, which is the transpose in this case. And you will also denote they don't use capitals anymore, lower script, where the column will then become the row. So the transpose of A in this case, 11, 12, 3, the column becomes row. So they're both vector, column vector and a row vector. It's just a special type of matrix. I want to remind you again that you get a special type of matrix, a square matrix, where the number of columns, rows equals the number of columns, and within that you get a special type of square matrix called a symmetric matrix, where the off diagonals match each other or are equal, and where the transpose equals the original matrix. Another type of very important type of square matrix is what we call a diagonal matrix. Remember that the diagonal would be the elements from top left to bottom right, diagonally across the square matrix, and a diagonal matrix would be a matrix only with a diagonal unequal to 0. The elements not on the diagonal, the off diagonal elements would be zeros. So A is then a diagonal matrix, a 2 by 2, with elements on the diagonal and zeros on the off diagonals. B, in this case, a 3 by 3. You can see on the diagonal 5, 3, and 1, and off diagonally only zeros. So again, square matrix, a symmetrical matrix, but a diagonal matrix. So a diagonal matrix will always be symmetrical because you only have zeros on the off diagonals. Another special square matrix would be a scalar matrix. A scalar matrix basically is a symmetrical matrix, but where the off diagonal elements would be zeros. So and the diagonal elements would be exactly the same number. So in these two examples, matrix A, you can see that on the diagonal you only have a 3, the number 3 on the diagonal, the position 1, 1, and the position 2, 2. And in the case of matrix B, you will see that on the diagonal you have exactly the same number 5 on the diagonal, and then obviously on the off diagonals the zeros. So this is then called a scalar matrix. So it's a symmetrical matrix, but it's a square matrix, but on the off diagonals you will have zeros. This then will basically conclude our first part before we get to some of the calculations in matrix algebra, and part 2 obviously then will follow on this first part.